Hi everyone, in this video we're going to be talking about the tangent and velocity problems. Let's start off with talking about average rate of change. Example 1 says, Mr. Kwon is on a road trip to see the Grand Canyon. He records the distance he traveled during various points on his trip. Refer to the graph below to answer the questions about Mr. Kwon's trip. So here we have our horizontal axis is using the variable t to measure time in hours, and then our vertical axis is using the variable s to represent position or distance in miles. Part A says, how far did Mr. Kwon travel in the first hour? And here this represents the first hour, and so we would look at this ordered pair here, and to answer our question it would be 77, and then make sure that you include the units. In this case it is miles because we are measuring a distance. Part B says, what was his average velocity during the first hour? So we are starting here, so I'm going to plot a couple of points or ordered pairs there. And this first point is the origin, 0, 0. And again, this point here is 1, 77. And if I connect those with a line segment like that, then essentially what we're doing to calculate the average velocity is we are finding the slope of that line segment. And so there are a few different ways that we can think about this. One way is using this notation delta, which means the change in. So you likely would have seen this if you've taken a physics class. So the change in distance over the change in time. We can also think about it using the slope formula, y2 minus y1 over x2 minus x1. So if I do that, I have 77 minus 0 over 1 minus 0, which ends up being 77 over 1, which is just 77. And notice that the thing that we're measuring in the numerator is distance, and in the denominator we have time. So if I want to put the units, then this would be miles over hours, or another way of saying that is 77 miles per hour. So here is our final answer for part B. Part C says, how far did he travel in the second hour? Now be careful, that means that we're just talking between here and here, and so if I wanted to plot some points, I'd have one here and I'd have one here. So to calculate the distance traveled, I would just subtract the y values. So for part C, I would have 100 miles minus 77 miles, and that would give us 23 miles. So there's our answer for part C. Part D asks, what was his average velocity during the second hour? So what we're going to do is something very similar. Let's change this to part D. So we have the average velocity is equal to the change in the distance over the change in time. So this would be 2 minus 1, and the units for this would be hours. So 2 minus 1 is 1. And so we get that the average velocity was 23 miles per hour. So there's our answer for part D. Part E says, is his average velocity higher during the first hour or the second hour? How do you know? Well, one way that we can tell is we calculated the numerical values, and so the magnitude of the number 77 is larger than the magnitude of the number 23. Also, I realized I highlighted the wrong values, so let me take that back. I meant to highlight these, so 77 and 23 miles per hour. So 77 is a larger number. And then kind of visually, another way we could tell is that if I put this here, so again, if I had a line segment to represent the first hour and a line segment to represent the second hour, I can see visually that the first line segment is steeper than the second one. So I know that it is the first hour for these two reasons that I explained earlier. For part F, it says how far did he travel during the first 2 hours. So now what I want to do is I can think about the origin as my starting point and this point as my ending point, and I can connect those with a line segment. So essentially, I just want to subtract the y values, and so that would be 100 minus 0, which is just 100 miles. G says what was his average velocity during the first 2 hours, and again, if we're going for, oops, this is part G. And let's see, we have 100 minus 0 over 2 minus 0, because this ordered pair here is 0, 0, and this one here is 2, 100. And so this is going to end up being, and simplifying to 50 miles per hour. Okay, part H says, what was his average velocity between hours t equals 1 and t equals 3? Okay, so I've put a point or ordered pair at 1, 77 and 3, 105. And so if I'm calculating the average velocity, again, there's several different ways you can think about it. I can use the formula y2 minus y1 over x2 minus x1, and I've labeled those there. So we have 105 minus 77 over 3 minus 1, and 105 minus 77 is 28 over 2. That ends up being 14, and the units for our numerator is miles, and then we have hours. So that is our answer for part H. We have 14 miles per hour. The average rate of change of the function y equals f of x between x equals a and x equals b, or over the closed interval from a to b, is defined to be the change in y divided by the change in x, or y2 minus y1 over x2 minus x1, or another definition, if we're using function notation, we can say f of b minus f of a divided by b minus a. The average rate of change is the slope of the secant line between x equals a and x equals b on the graph of f, that is, the line that passes through a comma f of a and b comma f of b. The word secant comes from the Latin word secans, which means cutting. A secant line is a line that intersects a curve locally at 2 points. Here we have a lovely picture to show us what's happening. We have that this thing here is our secant line. Note that linear functions have a constant rate of change, which we refer to as slope. Other functions have a variable rate of change. That means, unlike a line, the rate of change varies if you choose different points on the function's graph or curve. So I just happen to choose these 2 points here, a comma f of a and b comma f of b, but as I change those points, the slope of our secant line will change. So that's something to note. Suppose we want the difference between x equals a and x equals b to be some arbitrary value h. If that was the case, what would the question mark be on the graph? So what I'm saying here is I'm starting here at a, and I want the distance between my starting value and my ending value to be h. So that means that this x value question mark would need to be x equals a plus h. And I can erase the x part, so I'll just say that the question mark needs to be the value, or the x value, a plus h. Now that means that this here would be f of a plus h. So let's clarify. This first ordered pair would be a comma f of a, and then this ordered pair here, that's going to end up being the x value will be a plus h, and then the y value will be f of a plus h. So now, if I connected those 2 points and I wanted to find the slope of that line segment or that secant line, it would be y2 minus y1 over x2 minus x1, and I can label these. I'll call this one y2, y1, this would be x1, and this would be x2. So if I fill in those values, we would have f of a plus h minus f of a all over a plus h minus a. Now we can actually simplify this expression because this a and this a will cancel out, and so we get that the slope of the secant line is equal to f of a plus h minus f of a all over h. Now, if you look at this thing, it should seem somewhat familiar from pre-calculus, and this is just a variation of the difference quotient. So it turns out that the difference quotient is a way for us to calculate the slope of a secant line. Example 2 says find the equation of a line that goes through the point P, which has the coordinates 2, -3, and has a slope of -4. Then find a line that goes through P but is perpendicular to your original line. So we know that our point is located at 2, -3, and we have a slope of -4. So looking at this purple box here on the left, doing some review, I know that the point slope form of a line is y minus y1 is equal to m times x minus x1. Now here I can label this thing x1 and this one y1, and if I wanted to rewrite this in point slope form, my line, then I would get y minus -3 is equal to -4 times x minus 2. And I can clean this up a bit. This becomes y plus 3, which is equal to, if I distribute this -4 in, I get -4x plus 8. And then I can subtract 3 on both sides, and we get y equals -4x plus 5, and notice that this is in slope-intercept form. So here is point-slope form, and then this would be slope-intercept form. Now the second part says find a line that also goes through P but is perpendicular to your original line. And here it says 2 lines are perpendicular if they have opposite reciprocal slopes. What does that mean? Well, here my slope can be seen because this is y equals mx plus b. So here my slope is -4. And when it says opposite, that means the opposite sign. So we want the positive, and then the reciprocal means that you switch the numerator and the denominator. So we take the reciprocal. So for our other line that we want, the perpendicular line, that would be y equals, we take the positive and then the reciprocal, so that's going to be 1/4. And then x, and we also need it to go through the point 2, -3. So really, it would probably be more helpful if I use point slope form. So I'm going to do y plus 3 equals, so before we use -4, so I'm going to use positive 1/4, and then x minus 2. Okay, so I'm going to go ahead and distribute this, and we get y plus 3 is equal to 1/4 x minus 2 divided by 4, that gives me 1/2, and then I want to subtract 3 on both sides. And why are we doing this? This is just to put it into slope-intercept form. I also would have been okay if you just left it in point-slope form, which is that. But in slope-intercept form, we get y equals 1/4 x, and then if we found a common denominator, that would be minus 7/2. So here is our answer in slope-intercept form as well. So that's it for example 2. Let's talk about tangent lines. The word tangent comes from the Latin word tangens, which means touching. A tangent line is a linear function that intersects a curve once over a small interval and falls on one side of the graph. It doesn't cross the curve. Tangent lines follow the direction of the curve at the point of contact. So let's draw some. Example 3 says, draw the tangent line that goes through each of the designated points. What do you notice about the slope of the tangent line at each point? So here, one of my tangent lines would look something like that. Notice that it's just touching that point right there and not other places of the curve, at least in the general neighborhood of it. So here we have that. And then my next point, my tangent line would look something like that. Hopefully you draw a little bit better than me. For the next point, we have that. For the next point, we have that. And then for the last point, we have something that looks like that. Now, what do you notice about each of the slopes of these tangent lines? Well, some observations I'm making is this one looks like it's horizontal. So that would mean that its slope is equal to 0. Same thing with this one. It looks like its slope is equal to 0 because it's horizontal. This one, it looks like its slope is positive. This one, it looks like the slope of that line is negative. And then again, this slope looks like it's positive. So those are just some observations that we can make. Example 4 says, the point P, which has the coordinates 8, -3, lies on the curve y equals 3 over 7 minus x. And if you look here, this is actually that curve. So this is y equals 3 over 7 minus x. Oops, it's nice that it's graphed for us. And part A says, consider the point Q with the coordinates x, 3 over 7 minus x. Find m sub pq. M sub pq is the slope of the secant line that connects the point P and Q. Correct to 6 decimal places for x equals 7.9 and x equals 7.99. So let me illustrate what it is that we're doing here. On my curve, I'm going to try to make it a little bit further away. I'm going to call this point Q, and I'm going to say that it has the coordinates x, 3 over 7 minus x. And I don't know what x is, but it does tell us, well, why don't we try x equals 7.9 and x equals 7.99? So what I'm doing is I'm taking P and Q, I'm connecting them with a secant line, and then in my first instance here, I'm replacing x with 7.9 in both of these places. And then essentially, if I'm calculating m sub pq, that represents the slope of this tangent line here. So let's go ahead and do that. Okay, so again, for x equals 7.9, I'm trying to find the slope of the tangent line. And I know that my first point P has the coordinates 8, -3, and then Q, that point, it has the coordinates x, 3 over 7 minus x. But I want numbers for those because I'm trying to calculate a slope. So it's telling us to replace x with 7.9. So if I put 7.9 here, and then if I also put 7.9 here, 3 divided by 7 minus 7.9, I can simplify that as a number. So let's throw that into our calculator. So I went ahead and I threw that into my calculator, and that is equal to -3.3 with a bar over it, which means that that 3 repeats forever after the decimal place. So now that I've done these calculations, what I can do is I can label these x1, y1, etc. So it doesn't matter which one as long as you give them the same subscript. So what do I mean by that? Well, I could call this one x1, this one y1, this one x2, and this one y2. So the slope of my secant line is y2 minus y1 over x2 minus x1. And I'm going to go ahead and fill in those values now. So we have negative 3.3 repeating minus negative 3 over 7.9 minus 8. And I'm just going to throw that into my calculator. And if you throw this into your calculator correctly, you should come up with the number 3. And then it's going to be 3 repeating, but it says it wants it correct to 6 decimal places. So we would have 3.333333. Okay, so all of that was to find the slope of the secant line here. So this would represent the slope of this secant line where x is equal to 7.9 and then the y coordinate is equal to negative 3.3 repeating forever. Okay, that was a lot of work, and it wants us to do this all again for x equals 7.99. I don't want to have to go through all of that again. Is there an easier way that we could go about doing this? And the answer is abso-freaking-lutely. So let me show you a shortcut to doing this using our graphing calculator. Okay, so once again, I want to find the slope of the secant line between the point P and Q. And what we did last time was we took a particular x value, plugged it in for x here, and plugged it in for x here. But what if we came up with a general formula for the slope of our secant line? What do I mean by that? Well, why don't we call this thing, this expression here, y2, and I'm going to call this x2, and then negative 3 I'll call y1, and then 8 I will call x1. So again, if I want to use the slope formula, I have y2 minus y1 over x2 minus x1. And now for y2, instead of using a number, I'm using the expression 3 over 7 minus x, and then y1 is going to be minus negative 3, which is the same thing as plus 3, and then over x2, which in this case is x, and then x1 we labeled as 8. So what's the difference here? Well, previously we plugged in a specific value of x, but what's the advantage of leaving our expression like this? Let me show you on our graphing calculator, because this thing now is a function of x, and it represents the slope of our secant line. And now our calculator, our graphing calculator, is going to come in handy. All right, so here I have my graphing calculator simulator, and just notice that the key press history should show up down here so you can follow along with the buttons that I'm pushing. So I found a function to represent my slope of my secant line, and I'm going to go ahead and go over here to y equals so that I end up here. And now I want a fraction bar because I want to enter in my fraction. So I'm going to go ahead and press alpha and then F1. And if I press enter on this first option here, that should give me a fraction bar. And I need another fraction bar because there's a fraction in my numerator. So I'm going to go ahead and go through that process again. And remember, we're plugging in y2 minus y1. So I have 3 over 7 minus x. And then I have plus 3. And then my denominator, I had x minus 8. So how is this going to be helpful to us? Well, now what I can do is I can use the table feature. So I'm going to go ahead and go over to second and then table here, which is on the graph button. Oh, and right now my calculator is set to where I can't plug in specific x values, so I want to go ahead and change that setting. So I'm going to go ahead and press second, and then here, table setting, it's shortened, but I'm going to click on that, and then I'm going to scroll down to the independent variable. I don't want it to be automatic. I want it to be able to ask me what I want for the independent variable to be. So I'm going to go ahead and press enter on that. And now I'm going to go back to the table, and now it will let me plug in values. So why don't I plug in 7.9, which was the calculation that we did originally, and I want that to be a decimal. Let me see if it will allow me to change that to a decimal. Okay, that's not working. Let me see if I can fix that really quick. All right, so I'm going to go to mode, and then I want my answer in this scenario to appear as a decimal. So let's see if that will work for us. Awesome. Okay, so now when we go to 7.9, which we calculated earlier, we get the y value, which in this case, the y value represents the slope, is 3.3 repeating. Great. So now I can do the same thing for 7.99, press enter, and now we get that the slope of the secant line is 3.03, where the digits 0, 3 are repeating. So that's great. Let's go back to our notes. All right, so I just made a note saying when x is equal to 7.99, m sub pq, which represents the slope of our secant line, is equal to 3.030303 using our graphing calculator. Part B says continue your work from the previous question to fill out the given table. Okay, so notice here again, we're given an x value, and then we're asked to find the slope of the secant line. Sometimes students will get confused and they'll take this number and they'll think, oh, I just need to plug that into my function, which was 3 over 7 minus x. So if I plugged in 7.9, that would be 3 over 7 minus 7.9, which we found earlier. And I think we said that was negative 3.3 repeating. So that's not what we want to put here. Again, this is the slope of the secant line. So make sure you're computing the correct thing. So this is not what I want here. Going back, what we found the slope to be was 3.333333 because we're rounding it to 6 decimal places. And let's come back here. And we calculated it for 7.99. So now all I need to do is go into my graphing calculator again and do it. Now I just need to plug in 7.999 and the rest of these numbers. So I'll do it for a couple and then we can fill out the table. Okay, so I went ahead and I plugged in 7.999 and then 7 and then 4 nines after the decimal place, and I get these two answers here. I get that as well as that. And then in our table, we also wanted some values like 8.1, 8.01. And so now I'm just going to take these slope values and then plug them into our table in our notes. So let's go back. All right, so I've gone ahead and I filled out the rest of our slopes in our table. Part C says, using the previous table, make an educated guess about what the value of the slope of the tangent line to this curve that passes through the point P. So remember, these are slopes of secant lines, but do you see a pattern in terms of what they seem to be approaching? Because when our x values are getting closer and closer and closer to the number 8, and I'm going to introduce a new notation that we haven't seen in our class yet. I'm going to put a superscript with a negative, and that means that we're approaching the number 8 from the left-hand side. What's happening to these numbers? What are these numbers approaching? Well, as we get closer to the number 8, the slope is approaching the number 3. And then here, these x values, we're approaching the number 8 from the right-hand side because we're plugging in numbers that are larger than 8, but still getting closer and closer to 8. And similarly, these numbers seem to be approaching or getting closer and closer and closer to the number 3. So part C, I would make an educated guess to say that the slope of that tangent line at the point P, or that passes through the point P, I would say that that slope is equal to the number 3. Part D says, using the previous question, find an equation of the tangent line to this curve that passes through the point P. So remember, what we were doing is we were choosing some arbitrary point, and we were calling it Q, and we were finding the secant line, or the slope of the secant line rather. And then what we did was, well, what if we moved Q closer and closer to P, so that eventually it got so close, and then we are basically looking at the tangent line now, and based off part C, the slope of this tangent line is equal to 3. So now what I want to do is I would like to find the equation of that tangent line. So I'm going to use point slope form. So point slope form. And I know that I have, in general, y minus y1 is equal to m times x minus x1. And I can plug in some values. So I'm going to call this x1 and this y1, and then this represents m, our slope. So we have y minus negative 3, which is the same thing as y plus 3, is equal to 3 times x minus 8. And so this is our answer in point slope form. And if I want to change it into slope intercept form, I can distribute the 3. So that would be 3x minus 24. And then if I subtracted both sides by 3, so I'm going to subtract this by 3 as well, you would get y equals 3x minus 27. So this is in slope intercept form. Okay, so all of that was to find this equation of this tangent line. Let's go ahead and check our answer now with our graphing calculator. And this purple box here kind of illustrates how we can do that. So we can graph this function here. And like I said earlier, we could press alpha to get the fraction bar. And then let's see what happens from there. All right, so here we're back at our calculator. I'm going to go ahead and press y equals. I don't want the graph of this thing because this represents the slope of this secant line. So I'm going to go ahead and highlight the equals and then press enter on it. So now that means it's not going to graph that. And now I want to plug in our original function, which was, first I want to pull up the fraction bar. And then my original function was 3 over 7 minus x. And I have a feeling if I press graph, I'm going to want to change the window. But let's see. I'm going to press graph. And here, that looks kind of like what we had. I'm going to change the window because I don't want to see so many of the negative x values. So I'm going to change my x min to maybe -1. And then I'm going to press graph again. Great. And I'm going to change my x max because I want to see a little bit more of the x values, maybe to 14. Great. Okay, so this is how we draw the tangent line. I'm going to press second and then program, which would give me draw. And then I'm going to scroll down to option number 5, and then I'm going to press enter. And then now I'm just going to click 8 because I want to draw the tangent line when the x coordinate on my curve is equal to 8. So I'm going to press 8 and then enter. And now it draws the tangent line, and oh look, it gives me the equation, which is y equals 3x minus 27. There's a couple of digits kind of near the end, but that's, you know, if you round it, then we get y equals 3x minus 27, which is what we were looking for and what we came up with previously. Now that we have talked about average rate of change, we can start to talk about the instantaneous rate of change. An application of the slope of the tangent line is instantaneous velocity, or the velocity at an exact moment in time. Example 5 says, in an earlier example, we observed distances traveled over time. The equation that described our displacement is given by s of t is equal to 6t cubed minus 45t squared plus 116t. You found the average velocity between t equals 0 and t equals 1. You also found the average velocity between t equals 1 and t equals 2. Now we want to look at the instantaneous velocity at that exact moment that we have drove for 1 hour. That is, we want to find the slope of the tangent line to this curve at t equals 1. So here, t equals 1. If I draw the tangent line here, that will, if I find the slope of this tangent line, that will tell me the instantaneous velocity at that exact moment in time. If we want our tangent line to go through the point 1, 77, 1 is our t value. So when we're making this table here, we want to choose values that are really close to 1. So let's go ahead and do that. I'm going to go ahead and plug in some t values into my table. Okay, so I went ahead and I plugged in some t values that are getting closer and closer to t equals 1. Now what I want to do is I want to once again find the slopes of the secant lines where my fixed point, my p, is 1, 77, and then my q, the t coordinate or the x coordinate, I don't know what that is, I'm just going to call it t, and then the y coordinate is going to be given. Now we have our function. In the first example, we didn't have a function equation, but now we're given one. And so now we have 6t cubed minus 45t squared plus 116t. So again, I'm probably going to call this y2, this x2, I can call this one x1, and this one y1. So in general, if I want to come up with a formula for the slope of the secant line, I can do y2 minus y1 over x2 minus x1. The y2 value is this weird expression, this cubic polynomial, 6t cubed minus 45t squared plus 116t minus 77 all over t minus 1. So now what I should be able to do is I can plug this again into the table feature of my graphing calculator to get these values here. So I'm going to do that really quickly. All right, so I went ahead and in this third row here, I went ahead and I plugged in the slope formula for the new example that we're working on. I'm going to go ahead and go to table now, and I'm going to plug in some numbers, 0.9, and I'm going to plug in 0.99, and I'll continue to do that. Okay, so here is what we have. Let's go back to our notes. Okay, so what's the pattern? Well, these t values are approaching the number 1 from the left-hand side, and these t values are approaching the number 1 from the right-hand side. Do we see what the slope is approaching? In both of these columns, it is approaching the number 44. So what does that mean? That means that here our tangent line has a slope of 44. But what does that mean in the context of this question? Well, that means that in the exact moment at 1 hour, Mr. Kwon was traveling 44 miles per hour. That was his instantaneous velocity at t equals 1. Okay, so I went ahead and just boxed that and wrote that out. And that concludes this section. Thanks for watching.